In het laatste deel van een tweeluik over nieuwe kunstmatige structuren opnieuw aandacht voor 3 mannen die gefascineerd zijn door geometrische principes. Waar hun ideeën toe leiden, ziet u in Noorderlicht.
Structuren ontstaan als gevolg van een uitgebalanceerd krachtenspel tussen druk en spanning. En dat levert in de natuur vaak fraaie geometrische patronen op. Zoals deze stuifmeelkorrel onder de microscoop laat zien. Of een vliegenoog. Is het boek van de natuur geschreven met geometrische tekens, zoals Plato ooit zei? En als dat zo is, kunnen we die natuurlijke geometrie dan gebruiken om kunstmatige structuren te maken? Als het aan deze man ligt, wel. Hij denkt de natuur na te kunnen bouwen.
The Eyewitness News team. Now, Eyewitness News.
Tonight, Bill Clinton prepares for what could be the darkest day of his presidency.
Vlak voordat Clinton moest verschijnen voor de grand jury, kwam hij met een vreemd object in zijn handen de kerk uit. Een speeltje dat in de Verenigde Staten een ware rage is. Een speeltje bedacht door de ingenieur Chuck Hoberman.
Welcome to the Hoberman Toy Shop. This is an expanding sphere. It's made up of 6 intersecting circles.
And what's more to see in your toy shop?
Well, if we can make a sphere, we can also make a cube. And this is made of a special construction system for building expanding structures of all kinds of shapes. The one idea I had was I wanted to make an object that could disappear. That's what I thought about. Now, at that point, I was just finishing up my engineering education. I'd actually learned in school you can't make an object disappear. But what interested me was to get as close as possible to that idea, which is more or less the idea of having an object get as small as possible.
Chuck Hoberman is ingenieur en kunstenaar. Met behulp van origami, de Japanse vouwtechniek, leerde hij hoe hij objecten kon op- en uitvouwen. En dat bracht zijn technische geest op een heel ander idee.
This folded piece of paper was more than a piece of paper to me. I looked at it as being a little machine in and of itself. Why is it a machine? Because if you, say, apply force at different points, that force gets transferred through that folded piece of paper, and if I push on a couple of points, everything else moves synchronously. And in a way, that's what a mechanism is. It's a way of translating force, applied force, into motion, trajectory. So what that led to was when you, say, unfolded the piece of paper and it made a little shelter or whatever, you looked at it and you say, hey, there's a shelter, there's a building, there's a structure. So this piece of paper for me became 2 things. It was a mechanism and it was a structure.
Hoberman begon zeer ingenieuze schaarconstructies te bedenken en maakte vervolgens kunstwerken die zich op spectaculaire wijze kunnen ontvouwen. Zo ontwerpt hij ook stadiondaken die zichzelf als een bloem kunnen openen en sluiten.
The way that I think about my structures is a very specific relationship between maybe just a couple of links or a couple of pieces of the structure. So that those particular links or pieces have a very particular geometry that allows them to be connected to neighboring pieces, and those to be in turn connected to neighboring pieces, so that an entire shape is built up, maybe of hundreds or thousands of pieces. Now, what's the relationship of that to, say, nature? Well, I would say it's quite a specific one. It's the relationship of the part to the whole. nature is some way a kind of an aggregate of a lot of very complex processes that when we look at it, we see things change into other things. We see organisms grow and, you know, flowers unfold. And what's happening is there's very, well, there's a lot of theories about it, but maybe there are very simple rules that govern all of the parts. And in a way, that's the analogy, I think, to what I'm doing, is how parts add up to a complex whole.
In het Boston kinderziekenhuis onderzoekt de patholoog Donald Ingber de structuur van levende cellen. Hij zag onder andere dat de levende cel soms een fascinerend geometrisch skelet heeft. Dat zette hem aan het denken over de manier waarop de natuur complexe structuren bouwt.
People have known there have been patterns in nature for years. Geodesic architecture is probably the most common, where you see structures as simple as the buckyballs of carbon atoms in a perfect geodesic sphere, to viruses, to the insect eyes, to pollen grains, to in cells, we're saying the cytoskeleton. And then there's small parts of the cell that are organelles that are geodesic. And I think there are lots of books and papers written on, it's incredible, there are recurrent patterns in nature, but no one's ever seemed to ask why. And I think if you want to ask why, you have to begin to understand that the pattern is a structure. And if you want to say what holds a structure together, you don't want to know, is it made out of wood or particles or steel? You want to know what's the architectural design of it.
Met behulp van zelfontwikkelde computerprogramma's laat Ingber zijn medewerkers onderzoeken welke architectonische principes de natuur gebruikt om allerlei dynamische structuren te maken. En het is precies de dynamiek waarom hij zo gecharmeerd is van het werk van Hoberman.
I think the sphere, which can expand 30-fold in volume, just by changing the angles of its surface struts, is not so different from the way in which the surface membrane of living cells, which has other filamentous, an underlying filamentous scaffold. It's called the cortical cytoskeleton because it's at the cortex of the cell, that is made up of very springy molecules, but the molecules also can interact with each other and undergo volume changes not unlike this. So that has always intrigued me about his structures and his mechanisms. His folding structures is, again, a theme that nature uses during the insect body. When it forms, is a folding of solid plates. So it just is intrigued me as additional insight into some building rules that nature uses.
In zijn zoektocht naar het geheim van natuurlijke structuren kwam Ingber ook in contact met het werk van de kunstenaar Kenneth Snelson. Snelson is wereldberoemd om zijn ranke structuren die enkel en alleen bestaan uit buizen en draden en die hun stabiliteit danken aan een subtiel evenwicht tussen druk en trekkrachten. Ook Snelson is al zijn hele leven op zoek naar het wezen van de structuur. En dat komt in al zijn werk tot uiting. Zijn buizenstructuren worden alom geroemd. Veel minder bekend is dat hij jarenlang de kwantummechanica bestudeerde om iets te doen wat natuurkundigen streng verbieden. Namelijk een voorstelling te maken van één van de kleinste structuren, het atoom.
The atom is a fascinating mystery. Nobody knows what an atom would look like if we were able to see it. And we're told that we probably never will be able to see an atom in detail because the means for looking at it make it impossible to resolve a picture that tiny. So any image that we have of an atom has to be an invented one. We can take the information we know from secondary sources and try to conjecture. And people do this in all other realms when the information isn't readily available. In history, for instance, a lot of things you have to make up.
In de jaren 60 experimenteerde Snelson met magneetschijfjes. Hij maakte geometrische structuren door ronde magneten op elkaar te passen. Door die experimenten te combineren met gegevens uit de kwantummechanica kwam hij tot de conclusie dat elektronen, net als zijn magneetstructuren, een geometrisch en dynamisch patroon aannemen rond de atoomkern. Op die manier kan het atoom een stabiele structuur vormen volgens Snelson. En pas toen hij de beschikking kreeg over computers kon hij zijn ideeën volledig uitwerken en structuren ontwerpen die te ingewikkeld zijn om echt te bouwen. Hij kon eindelijk zijn idee over de structuur van het atoom echt goed laten zien. De elektronen kunnen volgens een strikte geometrie op vaste afstanden van de kern verschillende posities innemen. Dit zijn bijvoorbeeld de posities die een elektron in een waterstofatoom kan innemen. En zo ziet volgens Snelson een neonatoom eruit. Of koolstofatomen in een diamantrooster. Hoewel zijn model allerlei interessante eigenschappen heeft, kan het volgens de meeste natuurkundigen niet waar zijn. Omdat de standaardmening is dat het atoom zelf niet af te beelden is.
Why would one even want a visualization of an atom? Many physicists, for instance, think it's not only unnecessary, it's objectionable. They would rather have only algebra. But supposing that we had no visualization of the Earth, supposing that there were no Earth globe to refer to, so that you wouldn't understand that Japan was on the opposite side of New York on the sphere, we could get that information algebraically. You could actually describe something like that. But once you have an Earth globe, the mind says, "Oh, I see how it is." So I think that the atom, it would be desirable if we had such a picture for the atom as well.
And it's highly geometrical.
And it's, yeah, well, you know, atoms have to be highly geometrical. We arrive at wonderfully accurate pictures of molecules, how one atom connects to another atom in a molecule. And in crystallography, we find this geometrical perfection in, or near perfection in crystals. The whole thing has to do with geometry, to be sure. The mystery has been what kind of geometry. So this is my hat in the ring about a kind of geometry which is very attractive.
Donald Ingber is een grote fan van het werk van Snelson. Het zijn precies de geometrische eigenschappen van het atoommodel van Snelson die Ingber zo aanspreken. Want Ingber is ervan overtuigd dat de levende en de dode natuur opgebouwd is volgens geometrische principes. En waarom zou dat dan ook niet voor het atoom gelden?
I think he's right that there has to be structure at that level that we're missing with our mathematical depictions of models of the atom right now. I mean, to me, it's hard to believe that you can just jump one step in the hierarchy of life and find that all the rules that you see at all the other levels just stop applying. For example, we know that carbon-carbon atoms structure in very precise geodesic ways. We know the angles, we know the stiffness of the bonds. And to just go down from the carbon-carbon bond to inside the carbon atom and say it's all ethereal, this doesn't make any sense to me. I don't think anyone has been able to, no one has allied with Kenneth Snelson to, no physicist would approach it because it's so provocative, and to think how you could test that, which is, I think, is a pity, and I hope that someday that can happen, because I think he's onto something. I think, to me, I truly believe that it has to be a tension-dependent building system, because there is no compression at that level, no atoms touch. There are attractive forces. The precise structure of what it looks like is less important than the idea that it has to have some regularity of structure. And I think that the way he has modeled it can explain many of the interactions of atoms and how they create form and structure at higher levels. So I am very intrigued by it, and I'm supportive of seeing more.
De vouwstructuren van Hoberman deden Ingber sterk denken aan de manier waarop cellen zich kunnen vervormen. En het werk van de kunstenaar Snelson overtuigde Ingber van het universele karakter van de geometrie als bouwprincipe van de natuur. Dit en zijn eigen onderzoek naar levende cellen bracht Ingber ertoe om zelf nieuwe structuren te ontwerpen. nieuwe structuren gebaseerd op het werk van de natuur. Daarom richtte hij het bedrijf Molecular Geodesics op. Een onderzoeksbedrijf dat zich toelegt op het ontwerpen van nieuwe materialen.
We all share a common vision, I guess artistic vision of the beauty of pattern and structure. And each of them have explored it into great depth with great focus. And I've explored pattern and structure from how nature builds and the biology of it. And now with molecular geodesics, I think we're trying to leverage off of all of our insights and advances to try to think how can we actually show that structure can change the way we go about the world, whether it is building new industrial materials or healthcare, artificial tissues, new devices, new types of catalytic systems. So right now there's enormous excitement in nanotechnology, in material science, and getting stronger, better materials. But what nature does, at the nanoscale, what nature does is it builds at all scales. So it gets a further impact by incorporating architecture on top of the novelty of the material. And so the idea was, could we mimic how nature builds by structuring life at the nano, micro, meso, milli scales to provide materials that could be used for new aerospace materials, artificial tissues, surgical devices for minimally invasive surgery. And the way we approached it was to use computers to incorporate the design principles we were beginning to delineate by studying cells and tissues and just the whole hierarchy of life. And then developing what we call sort of a rational approach to material design, like people have done for drug design. And the idea is to take simple building blocks and simple rules and to let the computer self-assemble them into different configurations. But the computer can put them under analytical tests, mechanical tests for compressive strength, torsional strength, their porosity, surface area, how they can dissipate heat, what's the resistance to flow through it. And therefore someone can come in and say, I need a new airplane wing that can have all these specified functions and be in a complex curved shape. Just like nature said, I need a new bone with this complex curved structure and this shape. And I'm going to want to, store fluid inside of it. It's going to be the gas tank on the fuel tank on my spacecraft. I want to have in the body of it so that I have more space to do other things. And load that into the computer, and the computer will go through millions of different options of structures and select one. And that's what we're beginning to do. And then the real challenge is to develop ways to manufacture whatever you can precisely design in 3D on a computer and translate it into a three-dimensional material that is made of the right composition and has the right surface finish for what your needs are, whether it's metal for aerospace or a biodegradable for tissue engineering.
Computers die botstructuren ontwerpen. Of hele kleine mechaniekjes die een eileider van binnen kunnen afsluiten. Het lijkt allemaal science fiction. Toch slaagt Ingber er aardig in om zijn ideeën ook echt vorm te geven. Hoewel de techniek nog vervolmaakt moet worden, kan een aantal van die computerstructuren inmiddels ook echt gemaakt worden. En dat levert nieuwe materialen op met bijzondere eigenschappen.
Well, this is the simplest example that I can think of, which is it's a honeycomb replacement. In the aerospace industry, for example, honeycombs are required because they're one of the most efficient lightweight materials, and they are truly biomimetic. They mimic the honeycomb of a beehive. And those are hexagons with solid walls, which are very strong pushing down on the structure, but they don't have nearly as good a strength in different directions. They cannot be made into complex curved structures. And because they have solid walls, they're not very good in terms of letting gases or fluids pass through. This structure is made out of plastic it was fabricated using a rapid prototyping technique. It was literally built out of liquid, where a computer controlled a laser beam, an ultraviolet laser beam, that built layer by layer, a few thousandths of an inch at a time, out of a liquid. Wherever the UV beam hit, it induced polymerization in the liquid, and this then came out of a fluid bath. And this structure can hold 5,000 pounds, even though it only weighs a few ounces. It holds great. It can take over 40,000 times its own weight without failing. It also has spaces down the center. You could look down the center, and you could have pipelines of electrical cables, plumbing, et cetera, going through it. And it also is almost all air, so it can allow vacuums to go a vacuum to pull out quickly, or liquids to pass through. For filtration and catalysis, it produces a huge surface area to present enzymes. More importantly, it can be created in curved forms. For example, this structure is a sphere out of aluminum, and this is a complete sphere out of aluminum that's hollow and fully geodesic, designed on the computer. Whatever you see on the computer, you can see in a real material. This is a pipe that is a honeycomb that, again, you can maybe able to see through, that has two solid faces. Normally when you have honeycombs, you have solid plates that have to be chemically or physically welded to it. This is fabricated in a single unit, so you don't have leakage throughout.
It's not glued or...
No, this was fabricated as is. This is a solid piece. And so this is copper, and we're working on what are called countercurrent heat exchangers, which have fluids flowing on different planes to pull heat out of systems and to rapidly dissipate heat, which is another biomimetic principle. Life often uses countercurrent heat exchangers. We also have explored kinematic structures, such as this structure, which can expand greatly in its diameter just by changing the angle, similar to Hoberman-type structures. And this is of interest for minimally invasive surgery, where you want to go through a small 5-millimeter hole, go in, and then open up to create a surgical amphitheater or to open up a blood vessel.
De kracht van Ingber's ideeën lijkt te liggen in de combinatie van biologie, geometrie, kunst en technologie. En als we bij biologie niet alleen maar denken in termen van biochemie en genen, maar ook in termen van mechanica en architectuur, dan staan we volgens Ingber aan de vooravond van een nieuwe revolutie.
I do think that as we enter the 21st century, there is a renewed interest in dealing with questions of mechanics, architecture. I think it'll lead past the Silicon Age to the point where we develop, living circuitry. Because remember that there's nothing we can do with computers that come close to how animal brains function. And as we have the ability to control the way in which cells interact and connect and wire, and we can develop interfaces between living cells and more conventional machines, I think we will be into a realm of information processing far beyond what we know now. I think as we begin to develop algorithms that approach analysis by using the biological algorithms that are beyond genetic algorithms, that are not just saying all the information's in the gene sequence, but that are saying the information is in how all the elements interact. So we can deal algorithms that deal with complexity and architecture and structure, that we may begin to get the ability to deal with ways of predicting emergent properties, which is the essence of the building self-assembly of living system, and would be the essence of control systems and devices far beyond anything we have now.
Vooral in de jaren 50 en 60 werd archeologie in Israël toegepast om de identiteit van de nieuwe staat te onderstrepen. Met de op handen zijnde Palestijnse onafhankelijkheid luidt de vraag: maken de Palestijnen op dezelfde politieke en ideologische manier gebruik van archeologie om de nationale identiteit te creëren? Aan de vooravond van de verkiezingen keek Noorderlicht naar de geschiedenis van de archeologie in Israël en de eerste archeologische activiteiten op Palestijnse bodem.
Aber es wieder alle Fügen, alle Fügen. Ja, das sieht das hier mal so gut, ne? Ja. Und das geht mal aber so dann gut, ne? Ja. Sind so.